Good evening, everybody. Thank you all for coming down tonight. We are live from Books and Books in Coral Gables, Florida, so a note to our internet audience watching at home. If at any time you'd like to purchase a copy of tonight's book, just call the number on your screen. We will take care of that for you. We will have the author sign it, and we will ship it to wherever you are in the United States free of charge. For those of you watching overseas, the shipping charge might be just a little bit more. Well, this evening, Books and Books is very happy to present Mr. Ira Mark Egdall and his new book, Einstein Relatively Simple, Our Universe Revealed in Everyday Language. Mr. Egdall is the author of the e-book Unsung Heroes of the Universe. He is a science writer for DecodedScience.com, a website dedicated to explaining the latest science news in plain language. He recently retired from a 35-year engineering and program management career in the U.S. aerospace industry, and now teaches courses in modern physics he created at Osher Lifelong Learning Institutes at the University of Miami and Florida International University. In this book, with humor, enthusiasm, and rare clarity, he reveals how Albert Einstein revolutionized our understanding of space and time. From E equals mc squared and everyday time travel to black holes and the Big Bang, Einstein Relatively Simple takes us all, regardless of our scientific backgrounds, on a mind-boggling journey through the depths of Einstein's universe, bringing together for the first time an exceptionally clear explanation of how both special and general relativity. It is for people who always wanted to understand Einstein's ideas but never thought they could. Here to tell us more about it, please give a very warm welcome to Mr. Ira Mark Egdall.
Thank you. Welcome and thank you for coming Can everybody hear me? Yes. Can you hear me back there? Oh, great, thank you. I have to tell you that it's a special honor for me to be up here because I've sat in the audience like you a number of times listening to people talk about their books, and I dreamed that someday I would be up here talking about my book. One of those books, for example, is my friend Steve Benson. Want to raise your hand and stand up, Steve? He's an author friend of mine who wrote the wonderful memoir, Collision of Destinies. So it's a special honor for me to be here tonight. People ask me why I'm interested in Einstein, and in particular why I'm interested in modern physics. And the best answer I could come up with is shown here. The study of our current understanding of the fundamental laws of nature allow us to briefly peek behind the veil of human perception and get a momentary glimpse of reality. I find the revelation is always unexpected, difficult to accept because it violates our common sense very often, but ultimately wondrous. And that's what drives me towards my goal of trying to explain Einstein's theories and other aspects of modern physics to the general public, because I think these are things that are too important to just be known by the experts. I think everybody should know about them and understand them. As I was introduced, it's been told I teach late courses in modern physics, and most of my students have no background in physics. And they come because they're curious about the wonders of the universe and want to learn about these things, but haven't had any education in it. And I had a hard time finding a book on relativity that I could use for my relativity courses for my students. And they either were not clear enough or not understandable enough, or they were too watered down. So I decided to write my own book, a book which is comprehensive, understandable, most important, and also fun to read. And it tells how, the book basically tells how a former high school dropout revolutionized our understanding of space and time. The first part is on special relativity, which talks about how time slows and space shrinks with motion, how mass and energy are actually equivalent per the famous equation E equals mc squared. The second part of the book talks about Einstein's masterpiece, his theory of general relativity, and it reveals a cosmos where black holes trap light and stop time, where wormholes form time machines, where space itself is expanding, and where nearly 14 billion years ago our universe began in the ultimate cosmic event, what we call the Big Bang. Along the way in the book, We track Einstein through the perils and triumphs of his life, follow his thinking, his logic, and his insights, and chronicle the audacity, the imagination, and the sheer genius of the man recognized as the greatest scientist of the modern era. It is now my pleasure to introduce a surprise guest. Excuse me just a second. He'll be with you in a moment. Ignore the man behind the curtain. But I won't do to sell books, huh? Good afternoon. My name is Albert Einstein. Perhaps you have heard of me. Isn't it strange that I am such a popular fellow? But I must tell you, with fame, I have become stupider and stupider, which is a common phenomenon. And now I will try to work this. Yes. The most beautiful thing you can experience is the mysterious. It is the source of all true art and all science. Perhaps it is this curiosity with the mysteries of the universe which interests people to my discoveries. I apologize for my accent, it comes and goes. I was born, permit me to tell you a little bit about myself. I was born on March 14, 1879, in Ulm, a small town in the German Bundesland of Baden-Württemberg, bordering Bavaria. This is a picture of me with my younger sister, Marja. I did not speak, I am told, till I was 3 years old. The maid, she called me the dopey one. At age 5, I attended the local Catholic school in Munich. I was the only Jewish pupil. I was an excellent student, but in a world of my own. I was a dreamer. The headmaster of the school advised my father that it was unlikely that I would succeed in anything. At age 10, my parents enrolled me in the Leitpold Gymnasium in Munich. That is me, bottom row, third from the right. The school practiced a strict, formal, learning by rote method of instruction. The teachers, they were like drill sergeants. I hated it. I was a teacher's nightmare. I studied only what I was interested in. I was arrogant, bored, and stubborn, with little respect for authority. Hello? There it is. Thank you. My uncle Jacob inspired me in science and mathematics. I learned calculus on my own at the age of 14. But at the age of 15, I was formally expelled from the gymnasium for disruptions in class and disrespect for my teachers. I was, how you say today, a high school dropout. My parents, they were appalled. So I promised them I would study on my own, which I did, and then I took the entrance exams to the Zurich Polytech Institute, now called the ETH, in Switzerland. Please forgive me if I get confused. I am 136 years old. I failed the exams in French, chemistry, and biology. Subjects I did not care to learn, but I did very well in physics and mathematics. So I was sent to a small, progressive high school in Aarhus, Switzerland for coaching for a year. I then retook the exams, and this time I passed and was accepted to Zurich Poly in the physics math program in 1896. Hello? Oh, there it is. Okay. No, that's not. Okay, there we go. Oh, I was pretty good looking, yes? Yes. Oh. How did I do in college? As physicist Art Hobson put it, I attended classes sporadically and cafes regularly. The physics instruction was so old-fashioned it didn't even teach Maxwell's equations of electromagnetism, which were relatively new at the time. So my professors considered me arrogant and lazy. I did mostly private study on my own, but I did manage to graduate from Zurich Poly in July of 1900 with a grade of 4.91 out of 6. That low B. I was ranked 5th of the 6 math physics students in my class. Then I was unable to get a university position. I was the only one of the math physics graduates to be denied a job at Zurich Poly. My impudence and disrespect had come back to haunt me. My physics professor, Herr Weber, gave me a bad reference. I could not get a university position anywhere in Europe. I couldn't even find a job as a high school teacher. I was out of work for nearly 2 years. Then my college friend Marcel Grossman got me a job, hooked me up, as you say, with a job at the Swiss Patent Office. This is like magic, this thing. How's it? There it is, okay. Now that I had a job with a regular salary, I was able to marry my college sweetheart, Mileva Merrick, in 1903. Oh, I'm sorry, I skipped that. The patent office needed a physics professor who understood inventions in the growing field of electromagnetism. So I became an honorable federal ink pisser. I was a patent clerk, 3rd class, the lowest rank. I enjoyed my work at the office very much because it was uncommonly diversified, and I was able to do a full day's work in the first 2 to 3 hours. Then the remaining part of the day I would work on my physics ideas. When somebody would come into the office, I would take my physics notes and shove them into a desk drawer and pretend I was working on my office job. Then, now that I had a job with a regular salary, I was able to marry my college sweetheart, Mileva Merrick, in 1903. A year later, we had our first child, Hans Albert. Yes, it changes. I'm amazed. In 1905, I published my first paper on relativity. It is on special relativity. And the rest, as they say, is history. Now I am getting very tired because I am very old, and I will turn you back over to that other fellow, Mr. Egdall or something. Thank you very much, Albert. I appreciate your coming here today. Okay, now I'd like to do a little bit of explaining about, there it is, about one of Einstein's most impressive things that he came up with was time is relative. And I'd like to explain to you what that means. We hear this in newspapers, on the television, et cetera, but how many of us really understand what it means? It's been over 100 years since he came up with it, and I think it's time we all understood what the universe is really like. Special relativity is called special because it applies to uniform motion. What does that mean? It means a constant speed in a constant direction. Imagine you're on Route 95 with your car in cruise control, set at 60 miles an hour, and you're holding the wheel straight, so you're going in the same direction and in the same speed. That is what we call uniform motion. No change in speed, no change in direction. Special relativity applies to that special case of motion. Now, one thing that he said is time is relative. It slows down with motion. And I'll give you a simple example of that. Imagine my watch was super accurate, more accurate than even the best atomic watches. And imagine you all carried watches of similar accuracy. And if I were to move relative to you, right now, my watch and your watch tick off the exact same time. A second on my watch is a second on your watch, which is what you would expect. Now imagine that I'm moving with respect to you. And as I'm moving, you will see that my watch is running a tiny, tiny bit slower than your watch. You would see this. In fact, this has been measured in the laboratory down to about 20 miles per hour, and that's exactly what they see. Time slows down with motion. Now, if I were able to somehow get into a rocket ship and travel by you at something like 87% the speed of light, which is 680 million miles an hour or something like that, at tremendous speeds, you would see my watch running at half the speed of your watch. Every second on your watch would only be a half a second on my watch. That is relativity of time. Now, there's another relativity, which is the relativity of space. And let me give you a pen and take out a pen and show you this. Imagine you could measure this pen to extreme accuracy. You would measure a certain length. I would measure the same length, given we use the same instruments, given we use the same care. We would all measure this pen being the same length. Now, what if I move? Einstein tells us that you would measure, as this pen passes in front of you, you would measure and see this pen being a tiny bit shorter than it is when it's at rest, because space contracts with motion, just like time slows down. And if I was in that wonderful rocket ship again, going at 87% the speed of light, which I'll try to do without banging into anything, you would find that my pen appears to you, as it passes in front of you, to be half the length it is when it's at rest. So time slows with motion, and space shrinks with motion. And again, this has also been verified in groups of subatomic particles in the laboratory, that this is exactly what happens. And it happens to the formula that Einstein predicted it would happen. Now, unfortunately, these effects are not significant at everyday speeds. When we go at, say, 600 miles an hour in an airplane, which is probably the fastest any of us ever experienced, unless we're jet pilots, that is only 1/1,000,000th the speed of light, because the speed of light is 670 million miles an hour. So that at 1/1,000,000th the speed of light, Einstein's formula says the slowing of time and the contraction of space are so small they're almost impossible to measure. They have been measured with very, very accurate instruments, but our everyday experience, we don't notice it. But it is real. And it's only effective at speeds which are approaching the speed of light, which is 670 million miles an hour. Okay, so that's what Einstein's theory says. How did Einstein come up with such a crazy idea? Because it violates our common sense. But remember, Einstein said common sense is a prejudice. A prejudice we learn by the age of about 18, because it's based on our experience, and our experience is limited. We don't experience speeds fast enough to see that clocks slow down and space contracts with motion. It's all based on one simple postulate, simple but very, very profound, and that is that the speed of light, which uses the symbol c in physics, is absolute. Ignoring air in a vacuum, speed of light is always about 670 million miles an hour. In fact, light always travels at that same speed in a vacuum, no matter what the speed of the source of that light, nor the speed of the observer of that light. And as you will see, that has profound effects on time itself. Let us imagine we have an automobile here in the corner, and I'm going to shine its headlight. Now I will go over here, and let's imagine that I have a device in my hand that measures the speed of light. They have such devices. They're a lot larger than this. But imagine I have a device that measures the speed of light to great accuracy. And I put it right here so the headlights hit the light, hit the detector. What will I detect? I'll detect the speed. It'll tell me the speed of 670 million miles an hour. No surprise, that's the speed of light. Now, what would happen if that automobile was somehow able to rush towards me at 100 million miles an hour? What would be the speed of the light? Before I get the heck out of the way. What would be the speed of that light? 670 million miles an hour. The speed of the automobile, the source of the light, has no effect on the speed of the light itself. What if I took that automobile and put it in reverse and sped away from me at 100 million miles an hour? What speed would I measure? The same. 670 million miles an hour. That's his simple but profound idea. It doesn't matter what the speed of the source is. It also doesn't matter how fast I go towards the light or go away from the light. The light always measures at the same speed. Now, he came up with this by studying Maxwell's equations on electromagnetism and some of his own independent thinking. But basically, that is fundamental to special relativity, and this is how he built the whole world of relativity on this one simple but profound idea or concept. Now, let's think of that. And let's think of an example of a golf cart race as an analogy for what I'm going to show you later. Imagine there are two golf carts. One, a fella in a green shirt, and one, a fellow in a red shirt. And the fellow in the green shirt goes across from the start line to the finish line, goes across, straight across. The fellow in the red shirt goes at a diagonal. Who will win the race? The straight guy, the green guy. Yes, why? Shorter distance, yeah. Let's run the race. Very scientific race here. And the green wins. We're assuming, there's an assumption here, that they're both going at the same speed. We assume that the golf carts are such that when you press on the golf cart, both golf carts go at the exact same speed. So green crosses the finish line first. The diagonal path is longer, as many of you said, and so it takes a longer time at the same speed to cross. Very simple. Longer path, same speed, longer time. Okay. Now here's one of the brilliant things that Einstein came up with, and this is called a light clock. Totally impractical. But it's called a Gedanken, or thought experiment. But it teaches you about the physics. Einstein had said thought in pictures first, then in words, then in equations. So he pictured these things in his mind, and he came up with these simple, relatively simple, well, that's my book, relatively simple ways to describe the physics. So here's an example. He imagined a light clock, and this is Brian Greene's version. Some of you may know the great writer Brian Greene. Imagine a light clock containing two parallel mirrors. So there's a mirror on top and a mirror on the bottom, and there's one photon of light. Light is made up of photons, which is a particle, and you've got one particle of light bouncing up and down between the two mirrors, okay? So you imagine that, so it goes, and I like to think of it as going tick, tock, tick, tock, tick, tock. For those of you who are old enough to remember analog clocks, that's what they used to do. Tick, tock, tick, tock. So the clock goes tick when the photon hits the top mirror, and it goes tock when it hits the bottom mirror. Very simple. A light clock. Now we are asked to imagine two light clocks that are identical. One in the foreground that's at rest, and one in the background that's moving from your left to your right. Okay? So you have two light clocks. And what will happen with the light clocks? What will we hear from the two clocks? Tick tock, tick tock. Will they tick the same? No. What will happen? The top one would be slower. Why? It's moving, but what? Diagonal. Yeah, you guys are smart. Okay. The point is this. The bottom clock would go tick tock, tick tock, tick tock. The top clock would go tick tock, tick tock. It would run slower. And the reason is because the photon in the bottom clock and the photon in the top clock are both moving at the same speed. Remember, according to Einstein's principle on light, his light postulate, the speed of the clock has no effect on the speed of the light. Light always goes at the same speed, no matter what speed the clock goes at rest, moving, no matter what. So therefore, the top clock's photon and the bottom clock's photon travel up and down at the same speed. But the top clock's photon has to travel a diagonal path, doesn't it? To get from the bottom of the clock to the top of the clock. And therefore, it takes a longer time to travel the same path, for a longer path at the same time. An example is this, just to show you. Imagine the photon is moving between the two mirrors, up and down. Okay, now imagine I'm moving this light clock, okay? And as it's moving, the light clock ends up over here. So the photon now is up here, isn't it? How did it get from over there to over here? How did it do that? It went like this. If we could shut off all the lights in the room and just see the photon, you'd see, right? Right? That's a diagonal path. The diagonal path is longer than the straight up and down path for the stationary light clock, and a longer path at the same speed is a longer time. That's Einstein's clever and relatively simple explanation of this. The photon in the moving clock travels on a longer diagonal path, but at the same speed c as the stationary clock. That's the key. Because it travels at the same speed, at the longer path, it means it takes a longer time. The moving clock ticks slower than the stationary clock. Time itself slows down with relative speed. Okay? Isn't that strange? Time itself slows down. It doesn't just mean that a light clock slows down. My watch slows down. My aging slows down. Anything associated with time is slowed by motion. Anything. That's what Einstein is telling us. One of the wonderful things he did was he would take a very simple idea and with such great courage and brilliance, he would extend it to the universe. He would say, oh, it isn't just a light clock. It's all time slows down with motion. And every test we've done verifies so far that he is correct. Okay. Is it really true, people say? How can this crazy idea be true? If I've never heard of it before, I think you're nuts. Don't feel bad if you think this is crazy and if it's the first time you heard it. That's what physicists thought the first time they heard it in 1905. Einstein had a real hard time convincing the physics community that he was right. It was only till the evidence came in to support his theory that they said, oh, this guy has something to say about the universe that's true. For example, in 1971, many years after the 1905 theory was published, the first time clocks were actually shown to do this. That's how long it took technology to catch up to the theory. They took very sophisticated atomic clocks, Joseph Hafele and Richard Keating, and they flew them in airplanes around the world, first one way and then the other way to compensate for the rotation of the Earth. And they found that indeed the clocks did slow down in the airplane due to their motion relative to identical clocks on the ground by a very, very small amount. And when I calculated how much that amount was, it was very close to what Einstein had actually calculated. 10% accuracy, basically. There's also, by the way, a gravity effect, which affects time as well, and that also was verified in this experiment. So they showed that atomic clocks, real clocks, do slow down with motion. Evidence for time dilation was extended further with even more accurate hydrogen maser clocks on rockets by Robert Vessett and Mark Levine. They confirmed time dilation to 70 parts per million, his formula. Laboratory tests, a number have been done. The Great CERN facility did some tests in 1962 and 1985 in Helsinki, Finland, also down in Colorado in 1992, eventually extending the accuracy to 3 parts per million. Every test that we have come up with and done in the physics community has verified that time does slow down with motion and agrees to tremendous accuracy to Einstein's formula. Okay, another one is GPS. How many people have global positioning satellites, GPS, in their car or on their phone or somewhere around? It boggles my mind that you can have a little phone like this with GPS. What GPS does is it sends signals up and receives signals from satellites that are going around the Earth. These satellites have to have clocks that are very, very accurately timed on them compared to clocks on the ground. But the satellites are moving relative to the ground. You have to take into effect that time is slowed down by that motion up in the satellite as compared to the same time for the same clocks on the ground for GPS to work. You also have to take into effect the gravity effects on time. When you do that, GPS works. Without it, GPS would not work. So our GPS and the fact that it works is a continuous verification of Einstein's ideas and his formulas. Okay. What does it say? To me, it says that Einstein's crazy universe is our universe. By the way, this is a picture Albert Einstein did when somebody said to stick out his tongue, and it's also a life lesson. Don't take yourself too seriously. So we know that time slows down with motion, and now I'd like to talk about a relativity paradox, which really isn't a paradox. In principle, if you did this, what I'm going to show you, can your mother be younger than your own daughter? And in principle, we'll evaluate that. Can a mother be younger than her own daughter? Let's imagine Mama Kvetch. Maybe you have a mother like that, I don't know. Takes a round-trip rocket trip to a distant star at a speed of 99.5% the speed of light. No rocket ship today can go anywhere near that speed. I think, 20,000 miles an hour or something like that, was a small fraction of the speed of light. But we're imagining in the future we can get tremendous speeds. And I'm ignoring the effects of trying to accelerate up and accelerate back down. Let's say she could go at 99.5% the speed of light in this thought experiment. And her daughter Griselda remains on Earth. So what happens? What happens is when she comes back, the mother is younger than her daughter. How can that be? Is that really true? Does that really make sense from the physics we understand? And the answer is yes, it does. Crazy as it sounds. We have a rocket speed of 99.5% c, which is about 667 million miles an hour. Okay? And this time slowing effect is a very simple formula, the square root of 1 minus v squared, where v is a percentage of the speed of light. And if we stick in a percentage of the speed of light of 0.995, which is 99.5%, we square it, which means multiply it times itself, subtract it from 1 and take the square root. Everybody remember that from high school math? It's not nice to sleep in math class. We get an answer of 0.1, which basically says that due to its rocket speed, time runs 10 times slower on the rocket ship than it does here back on Earth. That's what Einstein's formula is telling us, based on that speed. The faster you go, the more the time slows down. Okay, now let's do a little simple arithmetic to figure out what happens between the mother and daughter. The daughter, Griselda, is on Earth. Let's say her age at the start of the trip is 25 years old. Oh, oops, don't go too fast. The round trip time, let's say it takes 30 years to get from Earth time, it takes 30 years to get that rocket to the distant star and 30 years to get back. And that's a total of 60 years. So how old is Griselda at the end of the trip? 85 years old, yes. 60 plus 25, very simple. Now let's look at Mama on the rocket. Mama is 45 years old, let's say, when she gets into that rocket ship and leaves Griselda. She's like 20, she had Griselda when she was 20 years old, which is understandable. And let's say, now what is the round trip time for Mama on the rocket?
6 years. 6 years.
6 years, absolutely right. 6 years. Why? Because time for her on the rocket is 10 times slower than time on the Earth. Everything on the rocket runs 10 times slower. Her time runs 10 times slower. Her supplies, she only needs 6 years of supplies. She won't run out of supplies in 6 years. Let's imagine, this is what I like to think of, let's imagine she takes a calendar with her and a very accurate watch, and every 24 hours she marks a day on the calendar. And every month she turns the calendar, and every year she puts up a new calendar. At the end of that time, she will find that 6 years have gone by. And she has aged only 6 years. So when she returns from that trip, how old is she? 51 years old. And this is real physics. This isn't science fiction. So Mama returns 34 years younger than her own daughter. Really strange. And there's something else about this that I want you to think about that I think is just amazing. Let's say the trip started at the year 2015, just for a year, okay? What is the year when, for Griselda on Earth, what is the year when the trip ended, when Mama came back? 2015 plus 60 is 2075. So on Earth, when we look at our calendars and Mama has come back and climbed out of the rocket and waved hello to everybody, and everybody says, my God, she looks so young. It is the year 2075, right? What does Mama on the rocket think it is? 2015 plus 6 is 2021. Her calendar, remember she flipped those calendars every month and then every year? Her calendar says it's only 2021. So from her point of view, from her perspective, of course she knows, because she studied relativity, what to expect when she gets back, but it's still very strange. It's still very strange. She comes back to Earth and everybody says it's 2075, and to her only 6 years have passed. And what it's like for her is that Mama has effectively traveled 54 years into the future. She's taken a 6-year trip and traveled 54 years into the future. Now, for special relativity, in principle, if you travel fast enough for only 1 year in a rocket, you could arrive back on Earth thousands of years into the future. And here's an example. If you took a round trip from Earth to a very distant star for 1 year at a speed of 99.99999% the speed of light, remember you can't reach the speed of light with anything that has mass, when you return, it would be the year 2236. I'm sorry, 2236 years later on Earth. You have basically traveled over 2,000 years into the future. In principle, there's no limit depending upon your speed. The faster you go, the further in time you come back, the more into the future you come back. Now here's the other thing I want you to take with you, and we talk about this in the book. We time travel. People say, oh, is time travel real? And I say, not only is it real, we do it all the time. We just don't notice it because the effect is so small. Anytime you leave your home and your person, your significant other, whatever, is at home resting, and you come back, you take a car and you drive, or you take a bus, or you take a plane, anything in motion, and you go to work, or you go to school, or you go to shopping, or whatever you're doing, and you come back, you also have to go in motion. That motion slows down your time, doesn't it? Well, tiny, tiny bit, billions of a second, but it is real. So your motion slows down that time, just like Griselda's time, and you arrive back at your significant other's or your spouse's house who has been at rest. You arrive back a tiny, tiny bit into the future. So every time you travel and return to the same spot, you are traveling into the future. So, in effect, we are all time travelers. Okay. Thank you very much. Okay, what I'm going to do next is, I appreciate you've been a great audience. What I'm going to do next is, if you'd like more information, please go to iramarkegdall.com, my website, and I'm going to do a Q&A session, and then I'll follow by doing a book signing. I'll sign books for anybody who would like to have their book signed, and please don't be shy about it. Just come on up, and I'd be happy to do it. Okay, any questions? Yes, sir.
Yeah, do you come back smaller too, like 50% smaller?
That's a good one. No.
No? Sure?
The rocket ship, only when the rocket ship is moving does it appear to be smaller.
Oh.
Does it measure to be smaller. But once the rocket ship comes back and is at the same, basically at the same velocity or speed as you are, then yeah, it basically ends up being the same size. It's only when it's in motion. Good question, yes.
There was recently in the news something about that they were proving Einstein wrong. They were about to prove Einstein wrong about some experiment. Are you aware of this?
The one in Italy? The
I think so.
The CERN
It was
experiment
in
in Italy?
Europe.
Yeah, the
What was it
neutrino
exactly
experiment.
about?
The results of that was very interesting. Physicists would love to prove Einstein wrong for two reasons. One, because it would mean new physics, which is so exciting, and two is whoever did it would be a Nobel Prize winner. They turned out to make errors in the measurement at CERN in this experiment with neutrinos, which they said seemed to go a tiny, tiny bit faster than the speed of light. They went a tiny, tiny bit slower than the speed of light. So once again, Einstein has been proven right. Einstein has survived over 100 years of experimental challenges and still does. Nobody's found him wrong yet. Maybe someday, but we'll see.
Make the news right away as soon as they.
Oh yeah, one of the problems is we live in a hyper-information age, and you can't, even if you want to, you can't keep the news out of the press. Somebody always spills the beans, and it gets into the press sooner than what you'd like. You'd like to have time to analyze and check and carefully do things. You can't do it these days. It's too bad. So sometimes science news gets out before it is mature, and we have to be careful what we read in the newspaper and wait to see 6 months, a year later, whether it's been verified. In this case, it was wrong. Okay, any other questions? Yes.
Yes, you did go into general relativity.
No, I do
That's
so
your
in the
book?
book. I do that. The book is two halves. First half is special relativity, which is what I talked about here, how motion affects time and space, and energy and mass. And the second half of the book is devoted to general relativity, and that is Einstein's theory of gravity and how gravity slows down time and stretches space. And I talk about that in the second half.
And also, just real quick, can you explain inflation, supersymmetry, and string theory?
And a few sound bites. Yeah, sure. All right, I'll try, but
Just repeat the question.
don't hold. Inflation, supersymmetry, and string theory. Very quickly. Inflation is the idea that we think we have evidence for, but they're not absolutely sure. That at the very beginning, the original Big Bang theory said that the universe itself expanded uniformly and is still expanding. And it's not something that's blown up into space. It's space itself which is expanding, which is a very strange phenomenon. Inflation theory says at the very beginning of the universe, the expansion of the universe was exponential. It went whoosh, tremendous expansion, faster than the speed of light expansion, and then slowed down to a rate close to the rate we have now. That's called inflation theory, and it has very good support. The second one is supersymmetry. Basically is an idea that there are all kinds of particles out there beyond the ones we know that are symmetric in some way with the ones we have now, and that is supposed to give us a simpler idea of how the electromagnetic force, the strong force, and the weak force are really the same force. No evidence for it, and so far all the supersymmetry studies have shown there's no evidence for it, so we just don't know. The third one was string theory. String theory is the most popular unsupported theory in history. We see it and hear about it all the time, and it's wonderful. But remember, there's not a single piece of compelling evidence to support string theory. There are mountains of evidence to support general relativity, special relativity, quantum mechanics. Those are established physics. String theory proposes that subatomic particles are really vibrating strings. And maybe they are, and maybe they're not. The point is we have to wait for evidence to say whether it's true or not, so I would remain skeptical. Yes, can I get one question? Any other questions?
This is a little off subject, but is there a relationship between the general theory of relativity and atomic weaponry? Was that part of Einstein? Was it all involved at all?
Atomic weaponry basically takes advantage of E equals mc squared, which is from special relativity. It basically says, special relativity. It basically says that contained within matter is an enormous amount of energy. In fact, matter is just frozen energy. It's just energy in a frozen form. And you can release it, and when you do, you multiply that mass of that matter, m, times the speed of light, c, squared, which means whatever the mass is times 670 million miles an hour times 670 million miles an hour to get this enormous energy. That's how the sun shines, and that is the basis behind atomic energy. Yeah. Any other questions? Yes, in the back.
Does that mean we're just a mass of energy frozen?
Yeah. In fact, one of the things I write about in the book that's very interesting is when you get on the scale and you weigh yourself and start to cry, most of the weight is energy. It's not the mass of the subatomic particles in your body. It's the motion of the subatomic particles, which is energy of motion. And it's the fields that they produce, which is energy, that produces your weight. Over 90% of your weight is really the energy inside your body, not the mass. Isn't that something? Any other questions?
Where can we get a tie like that is really
That's my wife. She picked it out. Any other questions? Yes? Yes, sir.
A matter of perspective, I read the special relativity part of your book, and I haven't gotten into general
thank
yet,
you.
And I enjoyed it.
Thank you.
You talk about, let's go to the time clock, which I think everybody understood.
Yeah.
If you are from the perspective of the moving clock, it would look like the whole world was going by you at the same speed, correct?
Yes.
So you would see the stationary clock moving slower.
I didn't say that because it's
Is that
people,
true?
but it's true. Let me go through
Now,
this again.
but I wanted to reconcile that with the space travel.
Yeah,
as well.
why one
If
ages?
you rocket away from the Earth and everyone's standing, you're stationary on the spaceship, and it looks like the whole
I'll explain.
planet of Earth is rocketing away from you. So why isn't it that you go back and you see everyone else's clocks change rather than from the perspective? You understand what I'm
Yes, I
asking?
do.
From the
It's a
perspective
common
of you.
question we all ask when we first study. Most people ask when they first study this. My watch is running slower. I said that, right? It's true, as you see it. What do I see? I'm moving at the same speed as my watch, aren't I?
Our clock's running.
I see my watch running normally, and I see it. To me, it's like when I'm moving this way, I'm really like thinking of you moving that way. See that? So I see your clocks running slower. So you see my clock running slower. I see your clocks running slower. That's what Einstein tells us. So if that's true, how about this Mama Kvetch on the rocket ship? We said her time slowed down, but doesn't she see that we moved? And the answer is in acceleration. It has to do with the fact that Mama Kvetch had to turn around. She had to slow down at that star, turn around, and speed back up to get back to Earth. In order to do that, well, let me give you another example. Let's say I do my watch, like let's say this gentleman here, we compare watches. I go over here, and I come back over here, and we compare watches again, okay? Well, we can't both be slowing down relative to each other. We either have to be the same or one of us has to be different. And what it is that because I am moving like Mama Kvetch, I'm moving in uniform motion, right? What am I doing now? Slowing down, turning around, speeding up, and then coming back. All of that is called acceleration. In physics, acceleration is any change in speed and any change in direction. Slowing down, speeding up is still considered acceleration. And if you remember, if you think about it, in an automobile, when you're going in uniform motion, you can't feel it. If you close your eyes in the automobile, you can't tell what speed you're moving at. 60 miles an hour, 20 miles an hour, 10 miles an hour, in a smooth road. As soon as the driver steps on the brake, what happens to you? You move forward. Stepped on the brake. As soon as he steps on the gas, you go backwards, don't you? Stepped on the gas. As soon as the driver turns the wheel, what do? You can feel acceleration that's different than uniform motion. And Einstein showed that it's acceleration which affects which of the two parties has the time actually slow down. And that's the answer to the question.
I see. So that supersedes the uniform motion
Yes, it does. Yeah.
calculation.
The uniform motion calculation is still there, but the acceleration calculation dominates.
Is more of an effect.
Yes, it dominates it and ends up explaining why the slowing
Gets it
down
straight
is.
in my head,
Yeah.
'cause I couldn't understand
No, I know, it's a difficult concept. And if you read part 2 of the book, you'll find that acceleration and gravity produce the same physical effects, and that gravity slows down time, therefore acceleration slows down time. And that explains it further.
Okay, thanks.
Yes, sir.
So if you have two rocket ships going in circles,
Mm-hmm.
counter to each other at the same speed,
Yeah,
and they pass each other, when they come around, they will always have the same time.
yes. Very good. Yes, they have to. Yeah, because they're symmetric. They have the symmetric acceleration. In fact, what they've done is they've taken subatomic particles called muons. Now, a muon is a heavy electron. It's just exactly like an electron in its electrical charge and all other aspects. It just has more mass. We don't know why muons exist. When it first was discovered, a great scientist, I think his name was Rabi, said, "Who ordered this?" And there are other heavy particles as well. But a muon, because it's heavy, nature doesn't like heavy, it automatically decays randomly into lighter particles, electrons, neutrinos, etc. And so this takes a certain amount of time, and it's called a lifetime of a muon. And when you take a muon in a place like CERN and run it around this ring, it's accelerating, isn't it? Even if the speed's the same, it's constantly changing direction to be able to go in a ring. And that change in direction is considered acceleration. And that muon has a longer life. It's as though if the muon had a watch on it, the watch would be running slower. And in fact, we've had muons that typically can run 10 times greater lifetime running around in this ring than they do when they're at rest. And that is exactly what Einstein predicted based on the speed. So we have evidence that acceleration is the reason why things slow down, whereas the muon in the jar doesn't. Very good question.
Okay,
Yes.
we have time for a couple more questions.
Okay.
from Mr. Egdall. Anyone?
I'm having fun. I'll go all night. Yes. Yes.
You know, now when you think about the Iraq War and all our wars that we're doing with cyber warfare and all the drones,
Yeah.
it seems like all of these theories should be put in effect, isn't it?
Huh?
When you think about the drones and how they're hitting their targets.
Well, I'm not sure how much of that has to do with Einstein's relativity. I would imagine the drones are going slow enough that we can use Newton's laws. I don't think Einstein's laws apply there. Yes?
How about the missiles that are shooting the anti-missiles, like the Hamas is shooting the missiles and Israel is shooting these missiles that target
Iron
them
Dome.
and
The Iron
catches
Dome.
them?
Yeah, I'm trying to think. The light is going obviously at the speed of light, so you have to take into account the speed of light there, but I'm still not sure. Based on the tracking of the missiles, it isn't just done with Newton's laws because they're still going so slow compared to the speed of light that you really don't need the greater accuracy of Einstein's theories there, I
The
think.
difference is not sufficient to make a difference.
No, it isn't. It's not sufficient to make a difference. I wish that we didn't need any of this technology, that all the human race would do it. Einstein, by the way, was a pacifist, an ardent pacifist. And he was even ardent pacifist to the point where he had enemies in the United States, and as well as other countries. And he wanted to see a world government and peace everywhere in the world. He was an idealist. So that's what I would hope someday we have here on this planet. Okay. Yes?
That he loved music and he played music when he was
Yes.
very young, and music was so instrumental in his being able to come up with ideas. Does anybody talk about how music, what it did to his mind to enable him to come forth with his ideas?
Yeah, I've read, and I'm not an expert on brain chemistry and brain science, but I play a bad piano. But I've read that the sites in the brain for music and the site in the brain for higher thinking in mathematics type of things are very close to each other. And my experience is that a lot of people I know in the technical fields are also into music and play musical instruments. And Einstein loved his violin, and they said he was a fair player for an amateur. You know, he wasn't that bad. And I think it gave him peace, and maybe the same talent that allows you to think and act in music helps you in the sciences and in mathematics. It may be true. Yes, yes.
He also, he had dyslexia as well, they say?
Yeah, they say he had dyslexia, but I'm suspicious, okay? And the reason is because they didn't test for it in those days. I don't even know if they knew about it in those days. So they're surmising that he had dyslexia. So he may have, but I don't think we know for sure. You know, but certainly he could have, and if he did, it just shows once again dyslexia has nothing to do with intelligence. You know, yes?
It seemed like he was well put together, had a good suit, his hair was okay. What happened to him at the end? It looked like he just let himself go.
No. Albert Einstein was a hippie. That's what we'd call him in my generation. He was a rebel. He was a bohemian, he called himself. He was nonconformist. When I dressed as Einstein, I was wrong because I have socks on. He didn't wear socks because he thought that was silly. He dressed sloppy. They had to really fight with him to put on a tie and a shirt. His hair was wild. Even as a young man, when he was very good looking, he dressed very unconventionally. So that was the way he was his whole life. Okay.
All right, thank you.
Okay. Thank you.
Just a quick reminder for our internet audience at home, there's still time to call the number on your screen. You could order a copy of the book. We'll have it signed for you, and we'll have it shipped to wherever you are in the U.S. free of charge. Also, a reminder that our live stream events are archived. So if you visit the Books and Books website, go to the live streaming link. Any author appearance that we broadcast from here at the store will be saved there for you to watch at your convenience. For those of you here in the house, we have the book for sale at the counter over there. Mr. Egdall is going to be signing at the table to the left of the screen, and that was really a lot of fun. Let's please give him another hand. Thanks very much. All right.